Alright, we're going to have a look at the normal distribution now, and the best way to look at it, I think, is just to dive in and do an example. And this example will illustrate the basics of the table and how to use the table to solve a problem. So, Rupert's Wireless Networks offers a 10 gigabyte data plan. An internal report shows that the amount of data used by subscribers is normally distributed with a mean of 8 gigabytes and a standard deviation of 1.5 gigabytes. So in questions, I'm not above throwing in some extra numbers that you don't need. The 10 gigabyte plan isn't really important to the question. The three things that we want to get out of the first read through is we want to know the mean, 8 gigabytes. We want to know the standard deviation, 1.5 gigabytes. And the fact that it tells us that it's normally distributed means that we can use the normal distribution. And we'll bounce them back and forth and use the table. But the first question says, what is the probability a subscriber uses less than 7 gigabytes? So I'll put out an approach, and as always, you're welcome to use your own method as long as I understand it. So the way that I like to do these problems is to start off by drawing a beautiful normal distribution. Maybe not so beautiful. And on my beautiful normal-like distribution, in the middle where the mean goes, I put 0 because a standard normal distribution has a mean of 0. And then just to give it some context, I'm going to put one standard deviation up and one standard deviation down. Now underneath this, I put a line that I like to call the measurement line. And on the measurement line, I'm going to put the actual mean, which is 8 gigabytes. And I'm going to go up a standard deviation. Now remember, our standard deviation was 1.5 gigabytes, so going up one standard deviation would be 8 plus 1.5, and that would take us to 9.5 gigabytes. Going down one would be 8 minus 1.5, and that would take us to 6.5 gigabytes. Now the question wants to know, what's the probability that a user will use less than 7 gigabytes? So on my beautiful diagram, or somewhat less than beautiful diagram, I'm going to shade the area that I want to find. So just to review, this normal distribution has an area of 1, and that area corresponds to probability. So an area of 1 is a probability of 1 or 100%. When we use the table that you're using in this course is a table called the cumulative normal distribution. What that means is it always starts in the very left-hand part of the curve and finds that area. So it will always find the area to the left of the z-score that you look up. Now to use this standard normal distribution, we don't want to know that it's less than 7 gigabytes. What we do want to know is how many standard deviations above or below the mean that is. And remember, way back in the first chapter, we learned how to do that, and that was called a z-score. So our formula for a z-score is z is equal to x minus mu, all divided by the standard deviation, which is sigma. Okay, and that is the formula that'll take us from this measurement line up to our z-score line. So let's plug in the numbers now. The number that we're looking for is that 7 that's written there. We know that our mean is just 8.0. And our standard deviation is 1.5. So we can probably do this in our heads. 7 minus 8 is minus 1, although I couldn't remember it in my head. And minus 1 divided by 1.5 is going to give us 0.6666 because the 6's go on forever. It's that, and remember there's a negative sign there. The first thing to know about your standard normal table is that it only works to 2 decimal places. So we're going to take all our z-scores and we're going to round them to 2 decimal places. So if we round that to 2 decimal places, it's minus 0.67 or minus 0.67. Okay, and up on our z line, we're right there. So what we want to know, that's one giant minus sign, is what's the probability we're going to get less than minus 0.67. So let's go have a look at our normal table. And what we'll do is we'll use this table. So if we look in the first column, it's got a Z there, and it actually gives us the units in the first decimal place. So we want 0.6 in that first column. We're right there now. And then for our second decimal place, we want 0.7. So right there, 0.2514 is the probability. So let's go back. So that 0.2514 is always the probability of coming out to the left of the z-score that you just looked up. So in this case, if they're asking you for less than a z-score, that's the area to the left, and that's what the table finds. So it's perfect. We don't have to do anything. There's our answer, 0.2514. Okay, so let's go have a look at B. And B says, what's the probability a subscriber use more than 10 gigabytes? And we'll see if my writing gets a little neater as we go along. It may or it may not. So, once again, I draw myself an awesome curve. It's already looking better. It's a way better curve. Yeah, I don't know about that line. Mean is 0. We'll go up 1 standard deviation, and just for fun, we'll go down 1 standard deviation. Down here, we'll put our number line to get some context. Mean is actually 8. If we go up a standard deviation, it goes to 9.5. If we go down a standard deviation, it goes to 6.5. And what we're looking for in this problem is we're looking for 10. And not only are we looking for 10, but we're looking for the probability that it's going to come out to be bigger than 10. So, next step is we'll find our z-score. So the number that we're looking for is 10, our mean is 8, and we're going to divide the whole mess by our standard deviation, which is 1.5. So once again, we can probably do this in our heads. 10 minus 8 is 2. 2 divided by 1.5. 2 divided by 1.5 is 1.33333333. Once again, round to 2 decimal places because that's what your table needs. And this time it's positive. Okay, so we are looking for 1.33. Now we're going to go back to our table and we're going to look up 1.33. So in the units, we look for 1.3, and for our second decimal place, we get 0.3. So 1.33 gives us 0.9082. Let's go back. So 0.9082 is the area to the left of our z-score. We don't want the area to the left, we want the area to the right in this case. So we remember that the total area under the curve is 1, so 1 minus 0.9082 is going to give us 0.0918. So the probability of a user using more than 10 gigabytes and going over the data plan is 0.0918 or 9.18%. So if you're looking for the area above a z-score, you have to go 1 minus the z-score. Let's go back and have a look at part C. And part C wants to know what is the probability that a subscriber uses between 9 and 11 gigabytes. So hopefully getting neater each time. Yeah, it doesn't look bad. That looks better. Go up 1, just for fun, we'll go down 1. Then we'll put our number line down here, 8 in the middle, 9.5, and 6.5. Now we're looking for the area between 9 and 11. So we're going to have to find ourselves 2 z-scores. So we'll do 9 first. 9 minus 8 is 1. 1 divided by 1.5 is going to be 1 over 1.5, which is going to round to 0.67. It's positive. And we'll do the next one. That's 11. 11 minus 8 is 3. 3 divided by 1.5 is 2, and just for good form, I'm going to write it down to 2 decimal places. And if we look up here, this is now 0.67, and this is now 2.00, and the area we're looking for is that area I've so neatly shaded. So the first thing we'll do is we'll go and look up 2. So 2.00, and there it is, 0.9772 there in the corner. So I'm going to go write that down. So 0.9772. And that 0.9772 is this entire area to the left of 2. Now let's go look up 0.67. And 0.67 is there, it's 0.7486. And that's the area to the left of 0.67. Okay, so one way to think about this is 0.9772 is the entire area, and 0.7486 is the area that we don't want. It's the area to the other side. So if we just subtract these two values, we'll get 0.22. Yes, it is. We'll get 0.2286. So whenever you have two z-scores and you want to know the area in between them, all you do is subtract the two areas. Now, one thing that you never do is you never add z-scores together and never subtract z-scores from each other. It's always probability that you're looking at.